with that, I think we can now close this and return to what we do best. Notes. So, what I just handed out to you is basically the lecture outline for the unit. As you can see, how much did we get through? We basically got through 6D. Only 30 more bullet points to go. Luckily, we got through the easy part. That's not lucky at all. So anyhow, all right. So what happens if you have an object move at a constant velocity? In other words, we want to be able to graph this thing. So how are we going to do that? Well, we go to the definition of average velocity, right? And what's the definition of average velocity? It's defined as delta x over delta t. And so a very easy way, so what does this mean? This means xf minus xi over tf minus ti, right? But I already went through and explained to you guys that, well, your position is generally going to be functions of what parameter? Time. So xf is actually x at tf, and xi is going to be x at ti, right, over tf minus ti. And then I said, all right, let's actually, enough with this nonsense. Let's actually talk about a starting time. And what did I call my starting time? Ti is, let Ti equal 0, and let Tf equal T. And so then our average velocity becomes V bar equals x of t minus x of 0 over t minus 0. So what happens if an object moves at a constant velocity? Well, if something moves at a constant velocity, what can you say about the average velocity? It would be constant and equal to whatever velocity it had. So you'd say if v is constant, then what we have is v bar equals v. And by the way, when I say v, what v am I talking about? Well, one of the things I'm implicitly saying when I say v is the instantaneous velocity, meaning the velocity at any instant is constant. Well, if the velocity at any instant is the same value, its average velocity is just simply going to be that value. So this is what you have. You have v is equal to x of t minus x of 0 over t. Well, what does that define in terms of x of t? What it defines is I can rearrange this, and you have x of t minus x of 0 is equal to vt. Anybody know what this is called? When I solve for x of t? This is called a linear function. In other words, for constant velocity, position is a linear function of what parameter? Time. For constant v, x is a linear function of t. Well, if it's a linear function of t, then the question is, what's the slope? Should be totally trivial. The slope is simply the... That's right, it's the velocity. So let's verify this. So one way to verify it is I'll go and open up Logger Pro. All right. And what I'm going to do is I'm going to take this thing and I'm going to start collecting data. And of course it doesn't work. This is the first lesson that you learn in physics experimentation. You ever hear the adage? What is it? How's it go? If it moves, it's biology. Right? If it smells, it's chemistry. And if it doesn't work, it's physics. So there you go. This is welcome to physics, guys. All right, so let's see this again. Oh, I know what's wrong with you. Hello. There you are. All right. So what I want to do is I want to for some reasons all right, so graph options. I would just want to enlarge this thing across the entire. There we go. And here we are. What? Erase. Physics works. So let me erase the data points that don't correspond to so now the question I have is notice, if I continue this line, where would it pass through? Would it pass through the origin, yes or no? The answer is no, it wouldn't. Why? Why wouldn't it pass through the origin? What would that represent? What does the intercept represent? Well, on the vertical axis, you have what? Position. And on the horizontal axis, you have time. So, looking at this, first thing you need to realize is where is the position 0 located? Can anyone identify it? Talk to each other. Where do you think the position of 0 is located on this thing? Do you know? I'm asking what on this thing here. When I'm asking where's the position 0 located, I'm talking about on this track. So you may need to get up and look at it. Don't be afraid to get up and look at it. Because what matters in physics is the apparatus itself. All right, very nice. So, do you want to repeat that to the class? So everybody take a seat. These guys got it. First one's up, got it. That thing right there is 0. So does it make sense that it wouldn't pass through the origin? Why? No. Think about, where did I physically start this thing? Where did I physically start that cart when I took measurements? I started the cart right around here. And I pushed it. Notice, how far was it away from the origin? About yay far. So the origin corresponds to where the position of this thing at time equals 0. And that's called a low friction track and a low friction cart. What does the slope of this thing represent? What is this? The average velocity. Be a little careful. It's the average velocity. So in order to actually do this, I'll go and do a linear fit. No, not for that region, for this region. Oh my God, why does it never work? So for this region, I'll do a linear fit, and there you have it. So the slope is 0.2780 meters per second. So if you have constant velocity, the average velocity generates a position function that has a linear function of time. So, any questions on this? So, let me make sure I go over this. Boom, boom. Now, let's go and do a problem. So looking at this, we have these three different indicators. These are three carts that are being plotted on the same set of axes. One of them is a diamond. Series 1 is a diamond. Series 2 is a square. Series 3 is a triangle. So looking at this, you guys should be able to trivially tell me what the average velocities of each of these are. So, take about 10 seconds and find the average velocity of each. So, anyone? What's the easiest one? Start the easiest one. Without question, which one of these is the easiest? Which one? Series 1, you think? Yeah, I'd say so. Series 1 is the easiest. Why? Because the change in position is 0, which means that its velocity is 0. It's stationary. Then let's say the square. What's the change in position of the square? I would do overall. Why not? So it starts off at, and it ends off at 15. So you have 15 minus -5 over what period in time? 4 seconds. So this is 20 over 4, which is 5 meters per second. Similarly, we go to the triangle. What's the final position of the triangle? -10. What's the initial position? And the time period's 4 seconds, so you get -20 over 4, which is -5 meters per second. Very trivial question. Nothing, nothing special about it. So now we go and look at this question. And this question's not so obvious. So what I should tell you is the initial positions. Okay. So what we want to know is what's the average velocity between t equals 1 and t equals 4? And what's the average speed? So how would I do the average velocity? Let's deal with the easy one first. The average velocity would be what? What's the initial position at t equals 1? It looks like roughly around 0, right? What's the final position at t equals 4? 2. So let me actually write this out. So this is x of 0, excuse me, x of 2 minus x of 1, sorry, divided by 2 minus 1. Notice I'm being very formal because you can get caught up in the numbers when you're looking at a graph. X of 2 is equal to, wait, I'm sorry, x of 4. I hate numbers. X of 4 is 2. X of 1 is 0 over how much time? 3 seconds, which is 0.67 meters per second. What's the average speed? So how am I going to find the average speed? Talk to each other for about 30 seconds. All right, so anyone think they have it? Yes.
Do you have to do the average speed for each segment, or it's from 2 to 1?
Well, remember, what's the definition of average speed?
Total distance over time.
Correct. It's the total distance over the time elapsed. So now we have to figure out what the distance is, right? So what was the procedure I said for finding distance? You have to go and you have to index every single point in which there was a change in direction. You have to index every point in which there is a change in direction. So where is there a change in direction? At what time? At t equals 3, right? So now, what is the distance it traveled? Or if you look at this, it's going to be the absolute value of x of 3 minus x of 1 plus the absolute value of x of 4 minus x of 3. Divided by the total time elapsed, which is 4 minus 1. What is x of 3? Yeah, let's say it's 3. What's x of 1? 0. Right? What's x of 4? 2. What's x of 3? 3. What do you end up with? 3 plus 1, which is 4 over 3. Any questions? Not obvious, right? Going back to what I was saying, distance is a tricky measurement. So, with that, I think we're done that. Now, let me define instantaneous velocity. And this is going to be a little rough for you guys, especially who here's had a year of calculus? All right, no one's had a year of calculus. That's fine. How many people have had pre-calc? So you may actually be somewhat familiar with this. So, if I have, let's suppose I have, let me take a new clean slate and lasso this and delete it. delete. All right. So I'm going to start off by reading the definition I'm going to give you, which is kind of the, what I would say, the wordy definition. So if a velocity function is continuous at a point in time, then the velocity function has a defined value at that point in time called the instantaneous velocity. What does it mean to be continuous? Well, that means on a very basic level, here's a more sophisticated definition of continuity, but on a basic level, it means that there's no gaps at a point. So if I were to give you a series of functions, let's say, you have v of t. Here are a series of velocity functions. v1 of t is equal to 3 meters per second for some time period. 0 less than or equal to t less than or equal to, I don't know. What time do I give? 5. Right? All these are different velocity functions. 2t plus 3, right? For t less than or equal to, I don't know, 16 and 0. v3, negative 5t squared plus 3t plus 2. T less than or equal to 8. And then I'll give you a crazy one, like, it's equal to 3e to negative 2t plus 2. And this is over 0 to 3. Okay? Notice all these have the same time interval between 0 and 2 seconds, right? They all share the same time interval between 0 and 2 seconds. Some of them go on longer than 2 seconds. Some of them go on way longer than 2 seconds. But you can at least say that they all share the interval from 0 to 2 seconds, correct? Now the question I have is, are these all continuous in that time interval? Say, are they continuous at 1 second? Do you see any major gaps? Are there any gaps when you go to graph these? Yes or no? Between 0 and 2 seconds. Yes, no? No, there are no gaps. In other words, these are nice, smooth functions that don't have abrupt gaps at any times in those time intervals. All of those define instantaneous velocities. In other words, you can ask when v1 of 2 is. What is v1 at 2 seconds? And at 2 seconds, what is v1 equal to? 3. You can ask what is v2 at 5 seconds. v2 at 5 seconds is going to be 13. On a very practical level, the instantaneous velocity is the velocity of this thing now. But of course, once you ask it now, guess what it did? Changed. What is that called? That's the nature of something called acceleration, which we'll study in a bit. So this is instantaneous velocity. So what would a counterexample be? In other words, what would be an example where an instantaneous velocity is not defined at a point? Well, it would look like something like this. Say v5 of t equals 3 from t equals t greater than 0, less than 7, and it equaled 5 at t greater than 7. So the question is, does this thing have an instantaneous velocity? Yes or no? And the answer is, at what point, Mr. Khalil? Because there is a point where it doesn't. And what is that point where it doesn't? At t equals 7 seconds. At any other point in time, this has an instantaneous velocity. But at t equals 7, it is both at, you would say it is both simultaneously at 3 and then at a split, at that splittest of a split second later at 5. It does not have a defined instantaneous velocity there. Despite the fact that this equation says that at t equals 7, it has a velocity of 3. It doesn't have an instantaneous velocity there. Questions? And one case where it definitely wouldn't would be this. Then it would have no value whatsoever at that point. So that is instantaneous velocity. Now let's actually go into some detail. So in order to go into some detail, I need to actually graph a more general position time function. And this is where things could get a little interesting for you guys. So let me draw this guy up. So let's suppose this is your position and this is time. And let me zoom in. Let me erase this. Okay. Let me actually make it nice and easy. Whatever. Last. All right, nice x in meters, and this is time in seconds. So here's your position time graph. Now what I'm going to do is I'm going to draw definitely a nonlinear function. So here's this nonlinear function. Okay? First question is the velocity constant? Yes or no? Definitely not. So, for starters, what I'm going to do is I'm going to take this time and call it t. And I'm going to take some later time and call it t plus delta t. So in other words, what is that span of time between t and t plus delta t? It's delta t. In other words, this right here is delta t. So if I were to ask you to tell me how to find the average velocity, how would you find the average velocity between t and t plus delta t? Well, the definition of average velocity is what? It's the change in position divided by change in time. So what is the change in position here? Well, what's this value equal to? What is that position value equal to at that point in time? It's going to be x of t. And what's this going to be equal to? It's x of t plus delta t. So when I look at what is the definition of slope? Slope is rise over run. So when I look at the average velocity is defined as the change in position, right? This is the initial, that's the final, divided by the change in time. And what's the change in time here? Delta t. So the change in time is delta t. But what does this specify? What does this thing actually specify? This specifies the rise divided by the run. Of what line? Of what line? What line is at the rise divided by the run of? The heat comes. It is the secant line between this point and this point. Well, what does that secant line look like? It looks like this. Ha! Get over here. Uh-oh. How do I move that thing? No, not panning. That's an object. How do I grab it? Let me grab it. All right, there we go. It's that secant line. So that secant line is the average velocity. This right here is the average velocity. The secant line is the average velocity. So what I'm going to do in order, can you have the instantaneous, is the average velocity defined at a point, yes or no? Can the average velocity be defined at a point? And the answer is no. By the very definition of average velocity, you need 2 points in time. So then the question is how can I find the instantaneous velocity? What can I do? Yes? Or in other words, I could take this and do what? Start collapsing the time interval. If I start shrinking this time interval, what happens to this secant line? Let me actually grab this. What happens to this secant line when I start collapsing it? Oh, God. What ends up happening, let me zoom in. That wasn't what I wanted. Let me see if I can get closer than 200. There we go. Maybe 400. Maybe 600. What? So there we go. If I take this thing and start shrinking this time interval, what ends up happening with that secant line is that it gets more and more, it starts tilting up more and more until it matches what line? The tangent line that passes through the point T. So if I'm going to define instantaneous velocity graphically, it would be the limit as delta t goes to 0 of the average velocity. Or in graphical terms, it is the tangent line to the graph This is not my friend. Did I just lose this? It is the tangent line to the graph at the point in question. So what this means figuratively, I'm going to go and throw this up on a new page. If I have the following graph. And I were to pick a sequence of points. This is x, this is time. Let's call this point T1. Let's call this point T2. Let's call this point right here T3. And I were to ask you to find the instantaneous velocity at T3. How would you do it? You would go and you would draw a tangent line through T3. Well, what does that look like? It looks like this. There's your tangent line through T3. The slope of that tangent line is equal to the instantaneous velocity at T3. Similarly, if I were to ask you the slope of the tangent line through T1, what would that look like? Roughly in your head, what do you see at T1? Yes. That's right, it's a flat line. Similarly, at T2, what would it look like? Which direction would it point? Yes. That's right. So we can redefine the instantaneous velocity as the tangent line, or the line tangent to a point in time on a position time graph. Questions? This is the time to ask, because we're going to develop this further. All right. So now, let's go back to the mathematical definition involving the limit. So what's happening is you're taking that average velocity and you're shrinking that time interval to 0. In other words, v of t is equal to, or defined as, the limit as delta t goes to 0 of v bar of t. Now remember, what's v bar of t? The average velocity, meaning it's the change in so in other words, this is of x of t plus delta t minus x of t over delta t. And you guys in calc right now should be able to recognize that. Anybody know what that's called? That's called the derivative. So now, here's a question. What is the instantaneous speed? What is the instantaneous speed? And the answer is the instantaneous speed, denoted by s, is equal to the absolute value of the instantaneous velocity. And so now here's the question for you. Why don't I have to account for changes in direction? Talk about it for about 15 seconds. Why don't I have to account for changes in direction? Anyone got it? Anyone got it? Want to volunteer it? I heard someone say the right answer. Go ahead. In other words, there's no time for it to change directions. There's no time for it to change directions. It's happening at a point. So the speed is simply going to be either it's just going to be the absolute value of the instantaneous velocity, depending upon whether the instantaneous velocity is positive or negative. So, with that, that's that. Now let's actually go through certain graphical quantities. This is more going into the theory of the graphing. Couple things. Everyone here has to go on to, I want to get some business done before class is over. You guys have to go on to WebAssign and take the WebAssign test, I think it's called. And what it is, it's just asking you a basic question like 1 + 1 = 2. And the whole point is I want to see if you're having any interface problems at home on your computers, so that you are ready for the full-blown assignment. All right. So, things you need to know about the graphical interpretation of instantaneous velocity. Well, one thing I think you were able to infer when I went through that small example regarding instantaneous velocity is if you have some position versus time graph, what do you notice about the points in time in which the instantaneous velocity is 0? What are the points in time where the instantaneous velocity is 0? Yes? Correct. In other words, where is it going to be 0? At what points? Doesn't matter. You can just point it out. That's right, at the max and mins. So in other words, the velocity, the instantaneous velocity is going to be 0 at what are called the relative extrema. So this point, this point, this point, this point. Notice I said relative extrema. What do I mean by that? Are they the extrema of this graph, yes or no? No. Why? Because the extrema of the entire function can occur at what points? It can only occur at one point, right? But what point can it occur at where the velocity is not necessarily 0? At the endpoints. So if you see here, where's the maximum value of this function? At the endpoint here. This is the maximum value. Is the instantaneous velocity 0 there? No. So that's one important thing that you need to know. So the zeros of velocity are going to be the relative extrema of position. Another thing you need to know is if I take, and this one is more important for theoretical reasons, that will become clearer later. If I take a position time graph, okay? And I take 2 points. So give me 2 points. Let's call this point and this point. So this is, let's say, A, t equals A, and t equals B. What is the average velocity between A and B? How would you categorize the average velocity graphically? You make a secant between A and B. So I'll go and make a secant between A and B. You're not going to do this to me again. How do I do this? Lasso. Okay? That line right there, the slope of that line is the average velocity between A and B. If your velocity function is, if your position is continuously changing over time, there exists at least one point in any interval such that the instantaneous velocity at that point is equal to the average velocity. What does that mean? That means there's going to be some point in this interval, roughly around there. Call that point T star. At that point, the instantaneous velocity, which is what? The tangent line, is going to be equal to the average velocity. So what does that mean? That means the instantaneous velocity is going to be parallel. It is the most important theorem in calculus called the mean value theorem. Basically, it says within any interval, there exists a point such that the slope of the line through that point is equal to the slope of the overall interval. Any questions? So in other words, the instantaneous velocity at t star is equal to the average velocity between A and B. So that's that. How much time do we have? 6 minutes. Relative velocity. So this gives us enough time to start relative velocity. And this is really where there's going to be the first conceptual issues. So everyone here drives in a car at some point, right? So if you take the red car and you take the blue car, clearly, which car is faster between the two? Question is, what does the blue car see? What does the blue car see? Yes. Okay, but what speed is the red car going? Is it going a speed greater than the red car's speed from your viewpoint, or less than the speed of the red car from your viewpoint? Yes. Then what? Let's take a look at this, right? What speed does the blue car observe the red car going? Faster speed than you observe, or a slower speed than you observe? Yes. Correct. The blue car is going to see the red car going slower than you would see the red car going. What is this like? This is like, I don't know, being on, let's say, what's the nearest two-lane road here? Nearest two-lane road would be? 24. Sure, 24 has 2 lanes at some point. Okay? If you're going in the right-hand lane at 20 miles per hour, and someone's passing you at 30 miles per hour, okay? Those velocities or those speeds are given relative to what? To the ground. So that means someone on the sidewalk is seeing you go 20 and seeing the other guy go 30. But what speed do you see that guy go? Yes. Correct. You see that guy going 10 miles per hour. Similarly, what I'm going to do is this. What does the blue car observe? Does it observe the red car going faster or slower than you see the red car? It sees it going faster. In that same vein, so now how would we actually represent this in terms of velocities? In other words, how do I represent the relative velocity? So how would I go about defining relative velocity?